Hello everyone, this is Whit from Brainstem Tutoring, and in this video we're going to talk about how to find the pH of a basic solution. So in this question, it says, what is the pH of a 0.25 molar solution of pyridine, which has the chemical formula there, and it has the Kb of 1.7 times 10 to the negative ninth. So you need to know that this is a weak base. You can tell by the formula, this nitrogen right there is super great at picking up an extra hydrogen as long as it's not super saturated or every single point of the nitrogen has too much stuff going on. But most people are going to bang on the fact that it tells us a Kb right there, that this is a weak base. So once we know we have a weak base, my brain goes here. We have steps of determining the pH of a weak base when the concentration is given and the Kb is given. That's a fairly vanilla, straightforward problem. Typical. So my first thing is I always want to start off with a chemical reaction. That will help us springboard into the next part of the problem. So when I have this chemical pyridine, which we may know a lot about, we may not, but we do know how every single weak base acts in water. So if this is an aqueous solution and it interacts with H2O, which is a pure liquid, it will reach an equilibrium with both the conjugate acid, C5H5NH+, essentially just slapped on the extra proton to the end of that, an aqueous solution, and the OH minus hydroxide ion, which is what happens to the H2O when you take away a proton. Wonderful. So we're going to start off with our ice table. We remember that H2O is a pure liquid and doesn't contribute to the equilibrium. This problem starts off telling us that we have a 0.25 molarity of that reactant, and we can assume that there's zero product to begin with. We have a fairly typical ice table that comes out of this with all 1:1:1 ratios that's forward moving. So we have 0.25 minus X for the equilibrium concentration of the pyridine, X for the concentration of the conjugate acid, and X for the concentration of the hydroxide ion. Our whole job right now really is to find the hydroxide ion. So we want to figure out X. At the end of every ice table, we can set up our Kb expression. Kb is equal to, in this case, the C5H5NH plus hydroxide over the original pyridine. And in this problem, we'll scoot back up to the top. We're told that this Kb is equal to 1.7 times 10 to the negative ninth, and it's equal to x squared over 0.25 minus x. All right, so we can do this approximation trick as long as the initial concentration, 0.25, is much greater, over 2 order of magnitudes larger than Kb, we can get rid of this minus x. I'm actually going to give ourselves some more space so I can keep on writing. So we have 1.7 times 10 to the negative ninth is equal to x squared over 0.25 minus x. But like I was saying, we can approximate, get rid of that. So we have 1.7 times 10 to the negative ninth multiplied by 0.25 under our square root will give us our x. Now technically, if you're thinking about in math terms, there should be a plus or minus there, but there is no such thing as negative concentrations that we're going to talk about, and so this will be the positive answer. And if you plug this into your calculator, you should get x would be equal to 0.06 times 10 to the negative fifth. Why is that important? Because it gave us our hydroxide. That's the whole goal of the acid problem, to figure out how much hydroxide is there. Once we have that, we get into the area of what I call the rectangle. We have this weak base. We're able to, with an ice table, figure out the hydroxide concentration. And our job is to get to the bottom left corner of this rectangle. And we're going to go this way and this way. We're going to figure out our pOH first. And then we know that pH plus pOH is equal to 14 at room temperature. So let's go back to our work. First of all, pOH, this is going down the rectangle. It's equal to negative log of OH minus concentration. When we plug that into our calculators, we should get 4.69 roughly. That is rounded. And then we'll be able to take 14 minus pOH will equal our pH. 14 minus 4.69. And we get, for our final answer, 9.31 for our pH. And of course, at the end of every problem, we should sit here and we should think. We had a weak base in a solution, so it makes sense that our pH is above 7, but probably not to that 13, 14 range yet because it's a weak base. Awesome. Well, I hope this was helpful. If you have any questions, reach out to us or leave a comment. And good luck studying for this acid-base stuff. Thank you.